This is the 18th video supplement for CIS 351, Grand Valley State University's course on computer organization and assembly language. This video discusses signed integers. In video 4, we learned how to use binary to represent positive integers in hardware. But what about negative integers? How would you use 4 bits to encode both positive and negative numbers? Pause the video and try to come up with a few possibilities. When asked to devise an encoding for signed integers, most students first suggest adding a sign bit to the binary number. In other words, add one more bit that indicates whether the number is positive or negative. This approach is called sign magnitude. Sign magnitude is appealing because it matches the way we naturally handle negative numbers. The sign bit is analogous to the plus or minus sign we put in front of integers when writing them out by hand. However, this approach has a couple of disadvantages. The first thing most people notice is that there are 2 bit patterns that both represent 0. In my opinion, this is more of a quirk than a problem, but it's still worth noting. The bigger issue is that sign magnitude breaks addition. And by breaks, I mean that the traditional longhand algorithm that we base the ripple carry adder on doesn't work. For example, look what happens when we use the traditional algorithm to add negative 2 plus 1. The resulting answer is negative 3, not negative 1. Now, we can certainly design hardware that will handle this problem, but it's usually better in the long run to avoid problems rather than handle them. So let's see if we can adjust our encoding so it works with the existing addition algorithm in hardware. Now, because our goal is to use the existing hardware, we'll use binary to encode the positive numbers. Why change something that's already working, right? Now let's pick an encoding for negative 1 that will work with the existing algorithm. And if it works with the algorithm, it'll also work with the adders we built based on that algorithm. All right, so let's start with negative 1 plus negative 1 equals 0. Given that we're using the traditional binary encoding for 0 and 1, what bit pattern do we need to assign to negative 1 to make the algorithm work? In other words, what sequence of 1s and 0s can we put in place of the x's in order for the addition problem to work out? Pause the video and try to figure it out. All right, let's work right to left. The rightmost sum bit is a 0, and the rightmost input bit is a 1. This will only work out if the other input bit is also a 1. Now let's do the same thing one column to the left. Notice by making the right input bit a 1, there's now a carry in to this column. With that carry in, the x must again be a 1 for the addition to work out. At this point, the next 2 columns are in the same state with an input bit of 0 and a carry in of 1. So after working out the value for each x, we see that the desired encoding for negative 1 is 1111. In other words, if you encode negative 1 as 1111, when you use the standard longhand algorithm to add 1, you get 0 as expected. We can apply this same reasoning to see that the encoding for negative 2 should be 1110. That's the encoding we need so that when we add 1 longhand, we get negative 1. Notice that if you carry out this process for the remaining steps, you get this. Let me point a few things out. First, remember from video 4 that in a very loose and informal sense, counting in binary represents the natural progression of bit strings. We begin with the bit string 0000 representing the integer 0, and then we map the next larger integer to the next successive bit string. Or in other words, as the integers increase in value, the bit string pattern moves forward. Again, remember I'm using the term forward in a very informal sense, hence the air quotes. This pattern of bit strings and values both moving forward is what we see for the positive numbers in both 2's complement and sign magnitude. But with sign magnitude, the bit pattern for the negative numbers moves backward as the numbers increase in value. It's this backward movement that causes the addition algorithm to fail when using sign magnitude representation. This may sound new, but you've seen this failure before. Notice that when computing negative 2 plus 1 in your head, many of you are mentally doing subtraction. I obviously can't speak for you personally, but when I do this, I mentally compute 2 minus 1 equals 1, and then place the negative sign where it goes. right? Our model of dealing with positive and negative numbers in everyday life is sign magnitude. And then when we do arithmetic with these negative numbers, we have to handle the negatives specially, like turning addition into subtraction. Like I said earlier, we could devise hardware that would work with sign magnitude and apply the algorithms we use when doing signed arithmetic in our heads. But in the long run, it would be better to pick a binary representation for negative numbers that would just work with the existing adders. So here's what we do. First, we use the standard binary encoding for the positive numbers. Then we take all the unused encodings, which happen to be all the encodings that begin with a 1, and assign the smallest one to the smallest integer, which is -8 in this case. And to be clear, when I say the smallest encoding, I'm talking about the encoding you would reach first if you started with all zeros and then followed that natural bit string progression. In this sense, the smallest 4-bit encoding that begins with a 1 is 1000. At this point, we move both the binary encodings and the integers forward to complete the table. And now we have an encoding that will work with the existing addition algorithms. Let me point out a couple more things. Notice that the range of a 4-bit signed integer is -8 to 7, or -2 cubed to 2 cubed minus 1. You might wonder why we chose -8 to 7 instead of -7 to 8, right? Why we put the extra number on the negative side instead of the positive side. Well, by choosing the first option, then we can use the most significant bit as a sign bit. Let me also mention the transition from -1 back to 0. This isn't so much a progression of the bit sequence as it is a rollover, like an odometer rollover. I don't see this as a special case. It's more just a convenience of how the math works out. So if you see a number in 2's complement form, how do you interpret it? How do you convert it to decimal? Well, first, remember how binary works. Each column is a power of 2. So when you have 1101 in binary, you have 1 times 2 to the 0 plus 0 times 2 to the 1 plus 1 times 2 squared plus 1 times 2 cubed, which is 13. 2's complement is similar. It just makes one change. The leftmost column has a negative value. So in this case, the place value of the leftmost column is -8 instead of +8. So what we're doing when we look at a 2's complement number, if it begins with a 1, we start with a negative value and count up. So in this case, we begin with -8 and move up 5 to get -3. Now what we're looking at here is the formal definition of 2's complement, the formal specification of what each place value is. However, in practice, when working with negative numbers, we use one of 2 shortcuts. The first technique is to flip all the bits and add 1. So for example, to write -3 using 2's complement, first we would write 3 out in binary, 0011, and then we would flip all the bits to get 1100, and then add 1 to give 1101. And if we place this back into the formal formula, we see that that works out to -3. Okay, now you try it. Pause the video and write -22 in 2's complement. Okay, so we write 22 in binary, 010110, flip all the bits, 101001, and then add 1, which gives 101010. We place this into the formal formula and we see that it does in fact encode -22. Notice that in the first step, when you write the number in binary, you need to include an extra leading 0. So there's room for the sign bit. +22 only technically needs 5 bits because the range of a 5-bit number is 0 to 31. But the range of a 5-bit 2's complement number is only -16 to +15. 22 is outside of this range, so we need a 6th bit. Now this technique of flipping the bits and adding 1 works in both directions. So try it out. What is 1001 in decimal? Well, flip the bits, 0110, add 1, that's 0111. So 0111 is 7, which means the 2's complement value is -7. Now try 101101. Well, flip all the bits, 010010, add 1, 010011, Well, in binary, that's 19, so that means our answer is negative 19. A second shortcut is to flip the bits to the left of the last one. Let's see what that means when encoding negative 3. So we write 3 in binary, 0, 0, 1, 1. The last one, in this case, is the rightmost bit, so we flip all of the other bits, giving us 1, 1, 0, 1, like we saw before. All right, now try it using negative 22. Okay, 22 in binary is 0, 1, 0, 1, 1, 0. This time, the last one is the second digit from the right, so we flip everything before that and get 1, 0, 1, 0, 1, 0. And like the first shortcut, this one also works in both directions. So use it to find the decimal value for 1100. This time only the leftmost bit gets flipped, which gives us 0100, telling us that this is the 2's complement for negative 4. All right, last one. What is 101100 in decimal? Well, flip the 3 leftmost bits. That gives us 010100. That's 20 in binary, which means we've encoded negative 20. All right, one last thought before we wrap up. Given a bit string, how can you tell if it's 2's complement or binary? Trick question, you can't. Remember, a bit string is just a pile of ones and zeros. There's nothing inherent in the string that makes it binary or 2's complement. Whether a string is binary or 2's complement is entirely a matter of how you choose to interpret it. That's why when you look at wires and pins in JLS, you see both the binary and the 2's complement value. There's nothing about a circuit that determines what the wires mean. Their only meaning is the meaning that you give them when you look at the wires. That may be a confusing idea for the moment. I remember it took me a little bit to get my head around it. We'll be sure to revisit it a few times throughout the semester. All right, let's wrap up. The main thing you should be able to do based on this video is, of course, convert between decimal and 2's complement, both directions. You should also be able to determine the range of values that can be represented using 2's complement with n bits. So for example, if I ask you what sign numbers can you represent with 6 bits, you should be able to tell me that you get a range of negative 32 to positive 31. And finally, you should also be able to explain the reasoning and the advantages and disadvantages of the different encodings we talked about, sign magnitude and 2's complement. In the next video, we'll see how to use these signed integers for addition and subtraction.